let's briefly go over what we were doing last time. So we were talking about all these properties of the stiffness matrices. We set up these global equations by assembling the local equations, local element equations. And then we said that if we want to enforce the boundary condition, then we just divide the degrees of freedom into two parts and enforce our boundary condition that way. We also took a look at some of the properties of these stiffness matrices. So briefly, we find that the stiffness matrix is symmetric. We said that it is going to be banded with a lot of zeros, so that's also sometimes called sparse matrices. We also said that it is going to be positive definite. So we said that the global stiffness matrix and the element stiffness matrix, they are going to be positive semi-definite, which means that at least one eigenvalue will be 0. And we saw that what does that 0 eigenvalue correspond to. So we found that if you take one element or if you take the entire bar, you can enforce equilibrium at any location. Just move the bar in a rigid body way. So those eigenvalues, the 0 eigenvalues and their corresponding eigenvectors, they represent the rigid body modes. And opposed to that, every other positive eigenvalue, that's the deformational mode. So the rigid body modes are removed when you enforce the boundary condition. So did anybody try to assemble the equations for the one-dimension code? Okay, so you guys got it, mostly? Okay. Yeah, so it's not that difficult, but just try to follow the code, and especially if you're confused about what the input-output variables are that I'm using in the program, use the Matlab Debugger, place a breakpoint right at the first line, and see how the code works. So once you place the breakpoint at the first line, you will see what are the values of x, what is the value of the body force, what are all these quantities that I created. And then it will be easier for you to understand where things need to be assembled and how. Okay. So anyway, then we also took a look at some of the convergence and accuracy issues in finite element, in one-dimensional finite elements. And a couple of points, we said that if you use a polynomial approximation of degree p, then the error in the displacement is going to be of the order of h to the power p plus 1, which means that we were using linear polynomials. That means p is equal to 1. H is the element size. So the error in the displacement was going to be squared of order h to the power 2, which means obviously that if you decrease the element size by 2 by increasing the number of nodes, the error goes down by 1/4. And similarly, we said that the error in the derivative, which is the error in the strains and the stresses, that is going to be of order p. So if we are using linear polynomials, this error will be the same order as the polynomials that we are using. For quadratic polynomials, when p is equal to 2, this error, the displacement error, will be 3, which means that if I double the number of nodes, then my error in the displacement is going to go down by 8 times. Okay, and the error in the stresses will go down by 4 times, because this would be h to the power 2. So similarly, if you keep on using higher and higher order polynomials, you can decrease the error, you can decrease h, which is the element size. You can still, so these are the two ways of decreasing the error between your computed solution and the exact solution. Okay, so last time we started to take a look at some of these variational methods. Now variational methods are an alternate approach to method of weighted residuals. And whenever you hear the word variational methods, you should think of energy methods. So we took a look at how we can apply these energy methods to calculate the displacement. So one way was this was the method of weighted residuals. The other way was this way. You construct the total potential energy, and you say that the potential energy for equilibrium should be 0 or minimum. So to calculate the minimum, you set the derivative of potential energy to be 0. And that gives you back the equilibrium equation. And so we started to take a look at how we would implement this for a one-dimensional bar, and we said that the potential energy for the one-dimensional bar is going to be this expression. Now, I've added some terms in blue. So if you have the handout from last time, these are the boundary terms that you can add to your potential energy function. So the total potential energy of the system is going to be the internal strain energy, which is right here, and the potential due to external forces, which is this and this. Okay. So these are nothing but the boundary forces at L and at 0. So this is the traction at 0, and this is the traction at L. So you can add these two terms, and you would get the potential for the entire system. Now to minimize this potential energy, we need to minimize this with respect to our displacement. So we were taking a look at the concept of directional derivative, which is also called the Gative derivative. And the way that this derivative is defined is like this. Now this is very important, very fundamental. So we will be using this kind of a thing again and again for even 2 dimensions, 3 dimensions, beams, plates, whatever. So this definition of the directional derivative is very fundamental. If you have a scalar functional j of any variable u, in this case our variable u is a scalar function of x, but it could be a vector, it could be a tensor, it could be anything. If you have a scalar functional j of some variable u, you want to take its derivative in the direction of a different u bar. So this was our virtual displacement, and that is going to be defined in this way. You just find the value of that functional at a variation of the u, and that variation is simply constructed by u plus some small number times that u bar. Okay, so you construct this new functional, take its derivative with respect to epsilon. This epsilon is a scalar, so you can always take a derivative of anything with respect to a scalar. Okay. Once you take the derivative, you put epsilon is equal to 0, and this is how you can calculate the directional derivative of some scalar function, some scalar functional of any set of functions, vectors, tensors, whatever. And just to give you some sort of a physical understanding of this, you consider this function f, which is a function of the position x. Okay, I'm defining this function to be x dotted with itself. So this is a function that represents concentric spheres in 3 dimensions, or you can just imagine that these are concentric circles in 2 dimensions. Okay, so as you go out of the out into the radius, the value of the function increases, and these are constants. Value of the function is constant along these circles. So we know that the gradient is going to be pointing radially outside, right? So the gradient is pointing radially outside, and that's what we get. If you calculate the gradient of f, you get twice x, and since x is radial, it's pointing outside. Now the interpretation of the directional derivative is exactly the same. You take the gradient, dot it with some general direction y, and what that will give you is the change in f if you move in a direction y. So let's say if I'm at a point here, and if my y is actually radial, then x dotted, this 2x dotted with y will give me the same maximum value of the gradient itself. On the other hand, if y is tangential, then x dotted with y would be 0. What that means is, if I move along the direction of the gradient, then the change in the f will be maximum. If I move perpendicular to the direction of the gradient of f, then my change will be 0. So this is just an interpretation or a physical interpretation of the directional derivative. And a very analogous thing also happens when you write it out for a functional of some scalar function u. So if you now try to find the minimum of the potential energy for the one-dimensional case that we had before, then this is just some calculations. You can go through those calculations in detail. But what happens is you take the derivative of the potential energy, you get back your principle of virtual work. And this should not be surprising, because that's the exact same thing that happened in our spring case. So where is the spring case? This is the spring. This was the potential energy. If you take the derivative of the potential energy with respect to the displacement, you get the equilibrium equation back. And this is the exactly same thing that is happening in one-dimensional problem. It will be the exactly same thing that will happen in 2 dimensions, 3 dimensions, beams, plates, whatever. Okay, so what I'm trying to tell you here is that once these concepts in mechanics are really very, very basic, very not that hard to understand. Once you get the concept, or once you can simplify the concept to some problem, some simple problem without oversimplifying it, you can actually extend it to higher dimensions, and extending it to higher dimensions is just mostly about some math, vector calculus, and that stuff. But fundamentally, the principles in mechanics are really that simple. So going back to this, we take the derivative, the directional derivative of the potential energy in the direction of the virtual displacement. We get back our principle of virtual work. So so to summarize what we just did, what we've done is this part. So we took our potential energy function, tried to minimize it in the direction of the virtual displacement. We got our this virtual work functional back. Now let's try to see if we can actually get the governing differential equation. So the idea here is that somebody gives you a energy function, that this is my total potential energy. Can you tell me what my equilibrium equation is? So if that's what you're trying to find, then you take the directional derivative of your potential energy, you will get some g. Now integrate it by parts in reverse. So what we are trying to do, if you remember what we were trying to do earlier in the method of weighted residuals, what we said was we integrate by parts to balance the derivatives. Here we are going to do the reverse process. We are going to unbalance the derivatives and try to take out u bar, or this u bar, common. And what happens when we do that is, if you take this term and integrate by parts this term. So to unbalance the derivatives, what we'll do is we'll take the derivative on this u bar, transfer it to the real displacement. And if you take the integration by parts of this, you will get this term. Okay, and in addition, you will get this boundary term. So now what you can do is you can take this u bar and this u bar common from these two integrals, and what you will get is this. So this right here, this one is nothing but your governing differential equation. So somebody gave you a potential energy function, you minimize that potential energy, you get your virtual work functional, you reverse integrate it by parts, and you get your equilibrium equation. Okay, so and you also get some boundary terms, but that's not really that important. So this is what this is what I just said, and since this is the strong form, if we follow this procedure, we can get the strong form. So in general, what happens is, if somebody gives you a potential energy function and you follow this process, you will come up with some differential equations. And those differential equations, those governing differential equations, are actually called the Euler equation or the Euler Lagrange equation, corresponding to the functional that you were given. So if somebody gives you a potential energy function, you minimize it, you unbalance the derivatives, and you calculate your governing differential equation, that is called the Euler equation corresponding to your functional. Okay. So here's the process, sort of in a flow chart kind of a way. This is the process that we just followed. So the real question is, now let's say we have this governing differential equation, which I'm, in general notation, I'm just denoting it with some operator, A. This operator could be a differential operator. So in our one-dimensional case, if this operator is the double derivative of u, then this would boil down to this equation. So in general, if somebody gives you a differential equation which has this form, we know how to construct this, right? How do we do that? This is from the method of weighted residuals. If we do the method of weighted residuals, we can go from the governing differential equation to the weak form. But the real question is, if you have this weak form, can you always construct this potential energy functional? And the answer to that is sometimes. What we need to decide whether we can have a potential energy function is a Weinberg's theorem. I'm not sure if anybody has heard of Weinberg's theorem here. Okay, so yeah, that's the theorem that will allow us to find whether there exists a potential energy function or functional or not. Yes. So the use of the potential energy is that it gives you a measure that a physical interpretation or a physical value for the energy stored in the system. There are some systems, actually, especially in molecular dynamics, where people start with the energy functional. It is hard to construct equilibrium equation for individual particles, or but you can construct Hamiltonians for those kinds of systems. If you can come up with a potential energy system, then you can convert it to a governing differential equation. But on the other hand, if you have this weak form, there will the physical interpretation behind this is not that important, but sometimes it is important to know that yes, this is based on some physics, that there exists a potential energy functional corresponding to your system. So that will help you also to actually solve the problem when you are solving that system of equations. It means that energy cannot be negative. So that means your stiffness matrix should always be positive definite. So those kinds of things are there when you can prove that a potential energy functional exists. Okay, but anyway, so to decide whether this potential energy functional exists, we need this Weinberg's theorem. And let's take a look at this Weinberg's theorem. So what this says, and if you take a look at actually the last page of the handout, there is an in-class assignment that we'll do towards the end. And that is basically the application of this Weinberg's theorem. So if there's anything that's not clear, just let me know right now, okay? So the Weinberg's theorem says that if you have some sort of a weak form, which can be expressed as G, U, real displacement, virtual displacement, then we need to check two conditions for G. The first condition that we need to check for G is that it is linear in the second argument. What that means is that it has to be linear in this second argument. And the way that we write that is G, the first argument, and we express the second argument as a linear combination of U1 bar and U2 bar. And if this quantity can be expressed as alpha, which is some scalar, times G of U and virtual displacement 1 plus beta, another scalar, times G of U times virtual displacement 2. So this is nothing but a statement of linearity of G in the second argument. Okay, And you can actually just, this is not that hard to verify. You can check that for our functional of the one-dimensional problem very easily. You can see everywhere that u bar exists, everywhere that u bar exists in the G expression. If it is linear, then G is linear in the second argument. The second condition is a little more tricky. What we want to say is that the directional derivative of G has to be symmetric in the second argument. So what we are essentially saying is that we have our weak form. If we try to calculate the directional derivative of that weak form in another direction, then that has to be equal to the weak form in that other, for basically u1 bar dotted with u2 bar has to be equal to dg of u2 bar dotted with u1 bar. So this is just symmetry of these two arguments when you take the directional derivative. So, and this is the definition of the directional derivative again for this weak form. Earlier what we had was the definition of the directional derivative for a single scalar functional. Here this is the definition that you will use for the weak form. So if these two conditions are satisfied, then we can conclude that a potential energy functional exists, and it can be calculated using this integral. So in this integral, all that we are saying is that take our virtual work functional, and t is again some parameter. And since it is a dummy parameter, because we are integrating over t from 0 to 1, this we can find out the potential energy corresponding to our G using this expression. So I think let's take an example for this. So this is the weak form that we had for our one-dimensional boundary value problem, right? So this should be familiar. This was the internal virtual work, and this term was the external virtual work that we had done before. And to check the first condition, you simply write that out, write this expression out, and you will see that everywhere that u bar occurs here, there's no other u bar term here. So it is linear in u bar. U bar occurs here, and there's no other term that has u bar. So this is linear. Again, in this, u bar is linear. So we know that G is going to be linear in the second argument. So first condition is met for our principle of virtual work. For the second condition, we will calculate the directional derivative of this G in the direction of u2. So all that we need to do is follow this definition. This was the definition of G, and if you write that out, you're going to see that the only thing that actually depends upon epsilon in this entire thing is right here, this one epsilon. And if you take the derivative of this term with respect to epsilon, then you're going to get this times c times u bar prime 2. And that's exactly what we have here. So let me call this expression by star, and let's consider the right-hand side of that second condition. So in the right-hand side, all that we have done is we've switched u1 bar and u2 bar. And once again, the only place that epsilon occurs in this entire expression is right here. So when we take the derivative with respect to epsilon of this entire thing, everything goes away except this term. So we have u bar prime right here, c, and u1 bar prime right here. And clearly, these two expressions are equal. So what we can say is that the second condition is also met. This quantity is equal to this quantity. That is, the directional derivative of G is symmetric with respect to the second argument, and therefore we know that a potential energy functional will exist. And to calculate this potential energy functional, we will just use the definition from the Weinberg's theorem. And this definition is also not very tricky. It's fairly uh, simple. It's just a little algebra. So you take the G functional. Everywhere that u occurs, you replace it by t times u. T is some scalar. And everywhere that u bar occurred, you replace it with u. And you have to add some constant because in general there is no datum for energy. How do you say when is energy zero, right? So if you have a system, you can add an arbitrary amount of energy, which is so that's why we will choose this constant, arbitrary constant, to be equal to 0. And so if you write this g function for these two quantities, what you will see is that you will get this. All I'm doing here is replacing u bar with u, so that comes here, and replacing u with t times u. So if you do that, this is the expression, and this is the exact same expression. The only difference is that there is a t sitting right here. And the next step is even easier. You have this t. Nothing else depends upon t. So all you need to do is to pull this t outside into this quantity. This right here just becomes your becomes a part of your potential energy functional. So if you calculate this t, integral from 0 to 1 t times dt, that is nothing but t square over 2. Take the limits from 0 to 1, what you will get is half. Okay, so you put that half here. This is nothing but your integral 0 to L strain times stress. So if I were to rearrange this, I could take this half inside the integral. So if I do that, this now becomes our strain energy stored in the bar. This is the strain energy stored in the bar. This is the potential due to external forces. So this was the same potential energy functional that we constructed using physical arguments. And we just saw that if you are given a weak form, you can actually construct this potential energy functional from the weak form by using this Weinberg's theorem. So all we are saying is that if our G satisfies certain conditions, we can construct this potential energy weak form, the energy form, which I'm denoting with E. So there is the strong form, which is the differential equations. Going from the strong form to the weak form, we use the method of weighted residuals. From the weak form to the energy form, we use Weinberg's theorem. Okay. All right. So now what we talked about till now was for statics, meaning there's no time-dependent effects, there's no inertia or anything. But obviously, like we talked about in our first few lectures, we said that div s plus b is equal to 0 in statics, and div s or div sigma plus b is equal to rho u double dot. That's the inertial forces. So the similar kind of things happen for when you are trying to calculate variational principles for dynamics, which just means that you are trying to build up an energy measure for dynamics problems. So this is the simple single degree of freedom mass and spring system. So those of you who have taken structural dynamics might actually be familiar with this. And if you write out the equation of motion simply from the free body diagram, you have some external force acting. If this displaces a u amount, then the spring force would be ku. The unbalanced force would be F minus ku. and that will, if that force, unbalanced force, is going to cause an acceleration which will be ma. So this is nothing but the Newton's second law. And if you write that out, this is the familiar equation of motion that we get for a simple single degree of freedom problem. So if you do this, you can do this using the free body diagram or the principles of equilibrium, or you can take the energy approach. So in energy principles for dynamics, we know that we can define a quantity kinetic energy, which is just half mv square, right? So v is the first time derivative of u. V is equal to u dot. So this is half mv square, and this is the potential, which is strain energy stored in the spring minus the potential due to external forces. So if you define your kinetic energy and potential energy in this way, then the Hamilton's principle, which is just another principle, energy principle for dynamics, what this says is define another quantity called a Lagrangian. And this Lagrangian is actually a function of two variables, the displacement and the velocity. So we are going to define this Lagrangian by saying that kinetic energy minus the potential energy. Now this is a little bit weird, because total energy stored in the system is kinetic energy plus the potential energy. And that is what a different dynamic quantity that is called a Hamiltonian. So but just to be consistent with your book by Reddy, most of the people also follow this Lagrangian formulation. So we are going to construct, or we're going to define this new quantity called kinetic energy minus the potential energy. And what Hamilton's principle says is that, now consider this particle u that at time t1 and at time t2. So from time t1 to t2, it is going to move, let's say, from this location to this location. Now this is an axis t. This is a one-dimensional problem, so it's just movement along a line, but the rate of that movement is what determines the shape of this curve. Okay. So this black line right here, that's the, let's say, the real displacement versus time. We are going to consider variations, virtual variations of that real displacement with respect to time. These are these possible two blue curves. And then the Hamilton's principle says that the directional derivative of this Lagrangian for all variations of this displacement should be 0. So if you do this, then you will get back the equation of motion for dynamics. So you can see that you just write out the Lagrangian, which is kinetic energy minus potential energy. This first term right here, this is the kinetic energy at u plus epsilon u. This was the definition of our directional derivative. So we perturb our real displacement by a small u bar, and we calculate the new kinetic energy. And we perturb the same, we perturb our u with some u bar, and we calculate the potential energy and the potential due to external forces. Now we calculate its derivative with respect to epsilon, and you'll see that the only terms that will contribute are this m, and there will be a 2 epsilon v, 2 epsilon u bar dot. That will come right here after you take the derivative with respect to epsilon. The same thing will happen here. There will be a derivative with respect to epsilon here that comes here, and this term is linear, so that just boils down to this case. Now if you take this term and integrate this term, this first term, if you integrate it by parts so that the time derivative moves from u bar to this, then what you will get is this equation. So if you take the integration by parts of this term with respect to time, then you will get this term. And now all you have to do is to take out u bar, u bar, u bar common, and you get your equilibrium equation. So this is the exact same analogy that we had in statics. You take your potential energy, or in this case the Lagrangian, you take the directional derivative of that Lagrangian, or you try to minimize that Lagrangian in time, and what you will end up with is the equation of motion. So this equation of motion is also called the same Euler-Lagrange equation, corresponding to the Lagrangian above. And in one-dimensional problems, I already mentioned this to you, that you can calculate this div s plus b is equal to rho u double dot. So this is the dynamic equation in one dimension. So if you have a bar, and if you are applying loads that are varying with time, then displacement, stresses, and everything, that those quantities are also going to be varying with time. And this would be the governing differential equation for dynamic problems. And similarly, this for 2D and 3D problems, we know that divergence of sigma plus b is equal to rho u double dot. This is something that we calculated in our first few lectures. So if all you have to do is to construct a Lagrangian and take its minimization using the directional derivative. This is a lot of math, but essentially you have to realize that the underlying physical or underlying physics concept is really not that complicated. Okay? All right, so let's do this in class exercise. Don't do it on the handout. Please take a separate piece of paper. And I guess we have 10 minutes. So let me just briefly describe the problem, and then when you're done, you can just turn it in, and we'll call it a day there. So what we are trying to do here is that we have this governing differential equation. So this differential equation is non-linear, because the solution u, which is a function of x, is being multiplied with its own derivative, and we take the second derivative of this. So this is different from the one-dimensional problem that we've been doing. This is a non-linear one-dimensional problem, if you want to think of it that way. So this is the governing differential equation, which should hold at every x between 0 and L. And the boundary conditions that are given to us are that this quantity right here, this quantity should be 0 at x is equal to 0. This is a natural boundary condition. This natural boundary condition will come out from the weak form. If you do integration by parts, it will come out naturally. So this is even for your homework problem 1, all you need to do is to take the governing differential equation, multiply it with theta bar or u bar, and integrate it by parts. Don't add any boundary terms. They will come out naturally from your weak form. And this, we are saying, is that the displacement, or whatever this function u is, has to be 1 at x is equal to L. So this is the essential boundary condition. This we do not include in our weak form, but all we do is we choose our u bar at L to be equal to 0. So this is the essential boundary condition on u, and this is the homogeneous essential boundary condition on u bar. So all that we have to do is to construct a weak form. All we do is take our equation, multiply it with a u bar. So you can see that this was the governing differential equation. I think I'm missing an f here. So let me write that term out. Minus u to L u bar f dx. So this is my weak form. And if you do the integration by parts, this term will lead to this term right here. Both the boundary terms, u bar at L is 0, and u bar or u prime at 0 is 0. So this entire boundary term goes away because of these two boundary conditions. So all we are left with is that this gu is equal to this term. And I think in your handouts there is a dx missing right here. So you can add that too. And let me add the body force term. So this is your virtual work, principle of virtual work for this problem. Now the question is, does a potential energy functional exist? And to conclude that, once again, you will use the Weinberg theorem, and all you need to do is to check whether those two conditions are satisfied for this G. If those two conditions are satisfied, then a potential will exist, and you can find it with the other with the expression that was given. So right now I'm not asking you to find PU or this pi, this potential energy function or anything. All I'm asking you is, does it even exist? So just check those two conditions, and you can turn it in whenever you're done.